Okay, I think we'll get started. So today we're going to talk about the second of the two dissipative processes that we'll be worried about. Last time we talked about friction, and today we'll talk about drag. These are very related. It's involved the motion through or against something. In friction, it's a force that opposes motion due to the contact between surfaces. And here, drag is a force that opposes motion as an object moves through a fluid. And fluid could be either anything from a gas to a liquid. Couple of key distinctions. What characterized a friction was that the frictional force was independent of the speed of sliding. It was also independent of the area of contact. So, and it also had two cases. One where before it starts to move, we have a higher coefficient of friction than once it starts to move. Drag has sort of different different characteristics. Drag definitely does depend on the speed of motion, and the area that presents itself to the fluid matters. And so there's a couple of nice distinctions there. Like friction, drag has two main cases, although there's a continuum really between them, but we'll look at two cases. All right, so we're going to focus in here on the drag force. Now this is always opposing motion. So if we're not moving, then there's no drag force at all. If we're moving this way, then the drag force is that way. If we're moving this way, the drag force is the other way. Now, there are two main components that make up the drag force. An inertial type force and a viscous force. So let's look at each of these individually. For the viscous force, what we have is this object moving in this direction. That's what this arrow means. And as it passes through the fluid, the different lamina, and of course this is a on pencil and paper bookkeeping way of talking about a fluid. But we can think about thin layers of fluid as individual lamina, and as the mass goes through, the object goes through, the lamina have to make way for that object here, but up here, the behavior is if there's really nothing going on. So there's a transition from the lamina going around the object up to as if there was no object there. And so we have these lamina of fluid. And and so the magnitude, now this is always opposing motion, but the magnitude of this force is going to be given to us by the viscosity, and we'll talk about viscosity in just a second. Then some kind of representation of the area of the object that's moving through the fluid. And then, and so this definitely changes based on the shape of the object or even the orientation of the object. So if this was moving this way, that would have a different L value than moving this way. So it's kind of a fudge factor for the different geometries. And of course, people in fluid dynamics and engineers who need to worry a lot about that have to make much more careful assessment of the shapes of the object. And then the speed right here, the magnitude of velocity. And of course, opposing motion. So let's talk about viscosity for just a moment. So we're kind of familiar with viscosity in a layman's terms. We think of syrup. If we pour syrup, we think of that as being very viscous, or thick motor oil as being viscous. And then we think of things like water as being less viscous. What viscosity is it's a measure of the fluid's resistance to differential flow. So if we think of those lamina again, what viscosity is telling us is how much the fluid doesn't like to have adjacent lamina moving at different velocities. And so how is that playing itself out here? And we will talk a lot more about viscosity in the higher level courses in the sequence, but that's good enough for now. So how's that playing out here? Well, as this object moves, because it seems like none of these lamina are moving, but they actually are. As this object moves, to a good approximation, the lamina that is right near the surface, the first laminated surface, is taken to be stuck to that surface. So that's moving along with the object. And then the lamina way out here, of course, wouldn't be moving. And so there's a gradient as we go in this direction of the flow of those, the differential flow of those lamina. And so if we have a really thick viscous fluid, that's not going to like that, and that's going to have a larger opposing force in this direction. If the viscosity is low, then that doesn't matter so much, this differential flow of these lamina, and so we won't see as strong an opposing force. So viscosity is the big deal here. And once we have a particular shape, if we go through a more viscous fluid, we'll experience more drag. Now let's turn to the inertial component. So we can think of, and this isn't a perfect picture, but we can think of the inertial component as this object is moving through this fluid. It has to press the air, let's say in this case, I should probably just say fluid here. We can think of like a baseball going through the air. It has to press this fluid more so on the front edge than the trailing edge. And because of that, we will get a resistance. There's going to be a restoring force back to the equilibrium that this air was in. And so as this pushes this way, this wants to push back that way. Now, what's interesting here is that, as you might expect, this depends on density. So the more of the fluid or air, if we're thinking about a baseball moving through the air, the more of that, then the larger this effect will be. So we would expect it to depend on that. We would also expect it to depend on this form factor or this geometric factor. Now notice this is coming in squared. And also notice, most importantly here, that the velocity is coming in squared. So this force depends on velocity in a different way than the viscous force. The viscous force is linear in velocity to the first power, and the inertial force is dependent on the velocity squared. Now these are captured in what's called a Reynolds number. Now I'm not going to say much about the Reynolds number because not sure if all of the physics books the general physics books are going to say much about it. It's a very important concept in fluid mechanics, but we're not going to say too much here. It's just a measure. We're going to just take it as a measure of the inertial versus viscous components to this drag force. And we're actually just going to look at the two limits. The limit of high Reynolds number where the inertial force dominates, and then low Reynolds number when the viscous force dominates. We're just going to look at those two extremes. A big deal in fluid mechanics is working out all these intermediate cases and really understanding the Reynolds number. But for us, for this course, we don't need to worry too much about it. What we do want to capture is the behavior of this drag force. And so we'll use D as our typical drag force vector. And so that'll be our inertial force. And so the formula that this sort of becomes is a formula that involves the coefficient of drag, so this will depend on the fluid. The density, that will also depend on the fluid, so this is the fluid density. And then the cross-sectional area that's coming into the fluid. So this is important here now. So that's giving some form to this. This is the cross-sectional area. And then the velocity squared. So if we think about or maybe in professional cycling where it's every just incremental gain in your aerodynamics can make the difference between doing well in the Tour de France or not doing well. The science that goes into presenting a cross-sectional area that's as low as possible is the main focus for that example. So if we can reduce the cross-sectional area, then we get better drag performance. That is lower drag. So let's plot this. Let's plot this drag as a function of speed here, and it's quadratic, so we get a parabola. And here's what I was mentioning there: if we have a better in terms of reducing drag in an automobile or in professional cycling, for example, then this curve is a softer curve, but nonetheless still a parabola. So you get these diminishing returns. As you go faster and faster and faster, you're fighting more and more drag, not just linearly, but quadratically. So it builds up pretty quickly. Let's just plot velocity again, but now think about two different fluids with different densities. And so again, if we have a lower density fluid, then we will have a softer curve, but nonetheless still a parabola. All right, so let's think about this idea of terminal velocity. So let's imagine here that someone jumps out of an airplane and is doing some, going to parachute out of an airplane. And so before the parachute opens, right, we accelerate very quickly, but at some point we reach what's called terminal velocity. And we are no longer accelerating, we're just falling at a particular speed. And that's because if we do the free body diagram here for this person, the weight stays the same. The person's weight is not changing as they're falling, but their speed is increasing, and we know that the drag force depends heavily on the speed, quadratically on the speed. So eventually the drag force will equal the weight force, and the net force, the vector sum of these two, since they're opposing each other, will be zero, and acceleration will stop, and we'll just be moving at a constant velocity. And that's terminal velocity. So we can find terminal velocity very simply by equating the magnitude of the weight vector with the magnitude of the drag vector, and then solving for the terminal velocity. And so that's just some algebra here, rearranging some terms. Now, we definitely want the parachute to open, because when the parachute opens, we're moving this way, the chute presents a much bigger cross-sectional area than our body does, and thus area here in the denominator, with the large parachute area, we dramatically reduce the terminal velocity, and we go to a speed that's safe enough for someone to land on the ground. And so that's a matter of increasing the area with the parachute. All right, let's look at the other limit here, where the viscous force is bigger. So that's going to mean the Reynolds number is going to be much lower. And a different structure to the force. We do see, as over there, we are linear in speed. And again, we have some kind of geometric factor here, this B value, and then viscosity, as we've talked about. So none of this is all that surprising based on what we said over here. There's a special case for a sphere, and that constitutes what's called Stokes' law. So there's lots of Stokes around. In this case, in viscosity, what's referred to as Stokes' law is the drag force here for a sphere. And notice the B, this is the B for a sphere. Now, you can utilize this to measure viscosity for high viscous fluids, and actually do a sort of a small rotations lab in physical chemistry, and one of the stations there is measuring the viscosity of corn syrup and glycerol through the Stokes method. And the Stokes method is one in which we drop a sphere into a column of viscous fluid, and we time how long it takes to go from one marker to another marker. So we just use a graduated cylinder, and we look at the top marker and the bottom marker, and then with a stopwatch we can time how long it takes to drop a sphere through the fluid. The sphere we use is a little round steel BB for BB guns, and they're nice and spherical. They're pretty uniform, so you take one. They're all pretty consistent in their size and shape. And so when you do this, you get good repeatability, and we can now compare two liquids. And let's see how that works. So what's going to happen here is we're going to have the weight force. It's going to be similar to this terminal velocity force, but there's going to be a buoyant force as well. And the buoyant force, which we haven't talked about here, but basically if you put something into, say, water, or in this case like corn syrup or glycerol, that's going to want to float that object if it can, and the force that it exerts is equal to the mass of the fluid displaced. So we take the volume of the sphere, that displaces the X amount of fluid, and that is going to be the buoyant force opposing the sinking of that sphere. So in order for this to work, we have to choose a sphere that's more dense than the fluid. We actually want it to be, for reasons I'll get to in a minute, quite a bit more dense. So the steel is much more dense than the corn syrup or the glycerol, and so it will sink, but there is a bit of buoyant force there. Now, as it drops into the fluid, just like the parachute, we will hit terminal velocity, and so very similar, we will set the drag force equal to the magnitude of the combination of these two, right? Because the net force has to be 0 at terminal velocity. We aren't fighting just the weight force. We're the weight force, but the buoyant force is helping us out in terms of what the drag is doing. And so we have to figure out this buoyant force. Well, we need the mass of the displaced fluid times g. And the mass of the displaced fluid is going to be the volume. I try to make this v look different than this v. So this is the volume v times the density of the fluid, and then times gravity, acceleration due to gravity. And then the weight is going to be the volume of the sphere. So these volumes are going to be the same, but these densities will be different. This will be density of steel, and this will be density of the corn syrup. These are common, though, G and V, and so we get GV delta rho. And delta rho is the difference in density between the steel sphere and the fluid. Now, instead of solving for terminal velocity over here, let's solve for viscosity and see how we can use this method to get the viscosity. So we could measure the viscosity absolutely if we carefully measure the sphere and measure the densities, which certainly is doable. And we would do so just by solving this equation, rearranging and solving for the viscosity. This looks more like an N here. This is a viscosity. But what is typically done is you have a known fluid with a known viscosity, and then you compare other fluids to it. And that way you can cancel out the sphere itself, all the details, and you just get ratios. And so if we look at the ratio of the viscosities, then to a good approximation, and this is why I had mentioned earlier we want the ball to have a significantly different density than the fluid. the delta rho, of course, will depend on the fluid. The steel will be the same, but for many fluids, particularly those that are essentially just hydrocarbons, the density is going to be roughly the same, something typically less than 1 gram per centimeter or per cubic centimeter, but roughly the same. And so to a very good approximation, so I'll just use an approximation symbol here, the delta density is the same, steel versus this hydrocarbon fluid. So then what the only difference comes in is the terminal velocity. And so we can measure this, the time it takes to go from line to line. That gives us our terminal velocity. Oh, and I should say the object reaches terminal velocity almost instantly when it's introduced into the fluid. Then we can rearrange this. If 2 is the known solution, then the viscosity of 1 is just the ratio of the terminal velocities times the viscosity of fluid number 2. And so that's a way we can use Stokes' law to measure the different viscosities of fluids in the low Reynolds limit. So that would be for viscous fluids. This would not work for, say, dropping a baseball off of a building. That's in this limit over here, the high Reynolds number limit. Okay, so between the last 2 lectures, we've learned about friction and drag. Both of these are dissipative forces that oppose motion. And friction, key ideas there. It's due to contact between surfaces. It's independent of area and independent of velocity. Drag is motion through a fluid. It is dependent on area, and it is dependent on velocity. It has 2 limits. One, the high Reynolds numbers limit, where the velocity dependence is quadratic, and then the low Reynolds number limit, where the velocity dependence is linear.